So we've been looking at derivative, and we talked about second derivative briefly at the end of the last unit, okay? And so we learned how to do a second derivative or third derivative or fourth derivative before, but now we're actually going to use it, okay? And this has application within a variety of contexts, but the basic application is in relation to the graph. And then, of course, whatever that graph represents, you can then apply it to that specific situation. All right, so, but when we're doing this, the second derivative, just to remind ourselves of the notation here, we're taking the derivative of the first derivative. So you may see it written like this, d squared y dx squared. Okay, you may see it written like this, or you might see it just written as y double prime. That's often how we would read that, y double prime, or f double prime of x. Okay, that's our second derivative. And then if we want more than that, we could have a third derivative or fourth derivative, and they become less and less useful the more you take the derivative. But you can do the third derivative or the fourth derivative, and typically we'll write it like this, and we'll just, in parentheses, we'll put the number of the derivative. We do it in parentheses so as not to confuse ourselves with exponents. Okay, so you have to pay attention to context there. The only one that sometimes we will still do with primes is the third derivative, but even that's starting to get a little messy. We'll do f triple prime, but a lot of times we'll just go ahead and write it like this, okay? Now, if I have a polynomial function, the nice thing is the more you take the derivative, the simpler it gets, okay? So if I take here the first derivative of f of x, we've got the 15x squared plus 14x minus 5. If I took a second derivative, I've got 30x plus 14. If I have the third derivative, it's just 30. And then if I do the fourth derivative, what is that? That's 0. What if I did the 100th derivative? It would still be 0, okay? So the nice thing is with polynomials, eventually it ends up being 0, and then every derivative after that gets down to 0 as well, okay? But that's just a quick reminder of how to get that second, third, fourth, whatever derivative. If we're dealing with other functions like a trig function or maybe a product, those are the ones that get more complex the more you take the derivative. Okay, just as a quick example here, suppose I had f of x equals, say, tangent x. Okay? The first derivative of tangent is what?
C squared.
Yeah, secant squared. But you'll notice now that I have a function in a function, the secant is in the square. So if I do the second derivative, I have to do the derivative of the square, which is 2 times secant to the first, but then I have to multiply that by the derivative of secant, which you may or may not remember. That one is secant times tangent. Okay, so the second derivative of tangent is 2 secant squared times tangent. Now, if I were to do the second derivative at this point, what am I going to have to use? Huh?
Well, this is the second product.
No, that's the first derivative.
Product and chain.
Oh wait, no, sorry, this is the second derivative. If I were doing the third, sorry, I forgot a prime. So if I were going to do the third derivative, I'd have to use the product rule, and inside that I'd have to use the chain rule, right? We'll only do the third one here. So f triple prime, or f third derivative, is, now the derivative of 2 secant squared is going to be 4 secant to the first, the derivative of the square, times the derivative of secant. So secant times tangent. And then that's the u prime, times v is going to be times tangent x.
Plus 2 secant squared x.
There you go, plus 2 secant squared x
Times secant squared.
times the derivative of tangent, so times secant squared x. Alright, so now notice what we end up with. We have a 4 secant squared x tangent squared x plus 2 secant to the fourth.
So do you keep going? That's
Yeah, let's keep going.
0.
So it's not going to go to 0. It's going to get more and more complicated. Now, you can kind of limit that a little bit if you do some trig identities. Okay? And just, I mean, you got to know these ones for sure, the trig identities. So like secant squared is 1 plus tangent squared.
Okay.
So if I wanted, I could convert all of this stuff to tangents, or using the same identity, tangent squared is secant squared minus 1. And that one actually might be a little more useful in this case. 4 secant squared x times secant squared x minus 1 plus 2 secant to the fourth x. And notice we have a 4 secant to the fourth minus a 4 secant squared plus a 2 secant to the fourth. So you see how I can actually simplify a little bit here? I've got now a 6 secant to the fourth x minus 4 secant squared x. So if I were going to do the derivative again, that might be a little bit easier because I'm just doing the chain rule twice, as opposed to if I did it up here, I'd have to use the product rule with the chain rule on both of those, and it'd be even more messy. But here's the thing, even doing this, it's going to get messy. Okay? So that's the nice thing about if you have polynomial functions, they tend to be simpler as you get the more derivatives. Trig functions tend to get uglier as you get the more derivatives. Okay? So that's just a reminder and kind of rehash of what the second derivative is. Let's practice one here. Let's get a second derivative of tangent of x cubed. Alright, notice I made the x cubed, not the tangent cubed. That makes it a little bit nicer. Okay, so go ahead and try this one. Okay, let's make sure everyone got the first derivative down. Okay, dy dx. We have a function and a function. What's the outer function? Tangent, okay? The outer function is tangent here. The derivative of tangent is secant squared. The inside stays the same. And then we multiply this by the derivative of the inside, okay? Some of you are not being careful with your chain rule, okay? This derivative shouldn't have been that hard at this point, okay? Now, one thing you will need to remember when you do your second derivative here is that the derivative of secant, this is not one you have to memorize for IB, but it's worth knowing. The derivative of secant is secant times tangent.
Just really quick, I know I'm skipping a step, but what if it's secant squared?
Well, what if it's secant squared?
2? I really don't
2?
know, I'm so confused.
Does it become secant squared x and times tan squared?
What do we have? No. What do we have to use if we have a
Oh.
function that's then squared?
Oh, you do the, I don't know the name of it,
Don't you put
but you do the first. Power rule, that's what it's called.
Not power rule.
the 2 in front of it?
Chain. Secant squared, the secant is inside the square. In fact, this right here is going to be a double chain because we got the x cubed in the secant and then the secant is in the square. Okay, we've done ones like this. Okay, just be careful, take it one step at a time, alright? Alright, let's take a quick look. If we're doing the second derivative, we've got to use the product rule, right? Product rule, because this is multiplication. So the derivative of the first part times the second, secant squared x cubed, plus the first part, 3x squared, times the derivative of the second. So let's work from the outside in. The outermost function is the,
Secant squared.
X
well,
cubed.
that's two different functions. It's the, which is on the outside.
X cubed.
No, that's all the way on the inside.
Wait, why are you
Secant.
taking the derivative
Period.
of secant squared?
Because we got to do the derivative of the second part, the u prime v plus uv prime. This is the v prime part,
Then
okay?
what's 6x?
The square, okay? The square is the outermost function. It's something squared. So the derivative of that is 2 times the something to the first power. Well, the something is secant of x cubed. Okay? So what exactly is inside the square? The secant. Okay, so now we've got to multiply by the derivative of the secant, which we just said was secant times tangent. But notice the x cubed is still hanging out in there. That does not change. Okay? Now we're on the inside. We did the square, then we did the middle, the secant. Now we've got the innermost function, so we need to multiply this by a 3x squared, the derivative of the inside, and that's it. Okay?
That's it.
We can simplify a little bit here. Okay, 6x secant squared x cubed plus, that's going to be a 9x to the fourth. Oh wait, not a 9, 18x to the fourth. Almost missed the 2. That's it. So plus 18x to the fourth. There's secant squared of x cubed, tangent of x cubed. Okay? I should have parentheses around that. So now that we've reviewed a little bit of actually getting the second derivative, let's talk about what it's used for.
Yay.
The first derivative tells us direction. Okay? Are we going in a positive direction, increasing, or are we going in a negative direction, decreasing? Okay? The second derivative is what we call concavity. Okay? Concavity. It's concave downwards if the second derivative is negative, and it's going to look generally like this. Or if the second derivative is positive, it's concave upwards. Okay? Now, remember that the second derivative is the derivative of the first derivative. So when the second derivative is positive, it's telling us whether the first derivative is increasing or decreasing. Okay? Get that into your mind right now. This can be a little bit tricky to really understand, but if you keep that in mind, that'll really help us as we try to interpret other things. Okay, so if my second derivative is positive, that means my first derivative is going to be increasing, and the original function is concave up. Okay? So just like the first derivative told us whether the original function was increasing or decreasing, the second derivative tells us if the first derivative is increasing or decreasing, and then we can go another step back to the original function. It tells us whether that's concave up or concave down. Now, think about this in relation to rate of change, okay? If we have a first derivative that's the rate of change, and then we take the derivative of that, what do we call it when we're talking about how much the rate of change is changing? Think about it with motion. What do we talk about if our velocity is changing? We're talking about acceleration. That's going to be the key application here with the second derivative. We could talk about velocity with the first derivative. Now we can talk about acceleration with the second derivative, and we'll talk about, okay, yeah, we're going this direction, but are we speeding up or are we slowing down? That's what we can use this idea of concavity or the second derivative to help us do.
Would the third tell us anything?
The third is actually, it's in physics, it's either called the jerk or the jolt. And the fourth derivative is the other one of those two. I can never remember which one is which.
It's like,
I think it,
And then they got cued on us and called the fifth, sixth, and seventh snap, crackle, and pop. So
What?
that's
No,
legit.
really.
So really they did. We never use it, but it's there.
that's amazing.
So.
I think
We need to use it somehow.
So now, let's think about this. This image right here, I think, will illustrate what I was just explaining. Okay? F prime of x is the rate of change of our position, velocity. Okay? F double prime is the rate of change of the velocity. Okay? So think about this. This downwards curve, you'll notice our rate of change, or the derivative, here it's positive, here it's still positive, but it's getting flatter. Now it reached 0. Now it's actually -1, and now it's a -2. So as we go from left to right, F prime is, it's decreasing, okay? It went from 2 to 1 to 0 to 1 to negative, or -1 to -2. It's decreasing.
So I found that.
So F double prime of x is negative. That's right. Okay? Now, if you look at this one, here the derivative is -2, then -1, then 0, then 1, then 2. So as we go from left to right, the first derivative is increasing. So the second derivative must be positive. Okay? Now, concave up, positive, looks like a smile. Okay? Concave down, looks like a frown. Alright? But sometimes you'll see parts that aren't quite as obvious as this, because you won't necessarily have all of it. Alright? Let me give you an example. And one example is our exponential function. Okay? We know the exponential, it has an asymptote over here. Okay, but it goes up like this. So the first derivative is always going to be positive because this thing is always increasing. There's no min point here or anything. However, if you look at the first derivative, it's really close to 0, but then it's increasing, 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 increasing. It keeps increasing forever. So the second derivative is also positive everywhere. And this is concave up. Okay? So that's another thing. You won't necessarily always see this nice little bowl or arch in completion, but it has that trend at least. Okay? All right. So So, when we were talking about increasing or decreasing, we had critical points, and those critical points told us when we changed from increasing to decreasing. In other words, it changed direction. Well, we don't have critical points when we're dealing with the second derivative. We have what are called points of inflection. Okay? Points of inflection. Now, a point of inflection, this is a term you should know, is this point here where our concavity changes. Okay? Now, pay close attention to this idea here. To the left of this point of inflection, okay, it's arching like this. And if you looked at the derivative, notice, is decreasing. It was positive, it goes to 0, now it's in the negatives. So right there, our second derivative would be negative. So this is concave downward, okay? F double prime is negative. This is concave down. Okay? It's concave down. Now, on the right here, you can see if we were to draw some of the derivatives, it starts out negative, then it hits 0, and then it goes to the positives. So the first derivative is going to be increasing. So that means F double prime is positive. And this is concave. There we go.
We're doing so good.
Concave up. The point between those is the point of inflection. Okay? Now, a couple notes about points of inflection. In order for there to be a change from positive to negative, somewhere it's got to hit 0, right?
Right.
So, the point of inflection is where the second derivative equals 0 and then changes concavity. Okay? Just illustrating over here on this second one. Notice here we have a plateau point. Guess what plateau points are?
Points of inflection.
They're also points of inflection. Okay? Now, not every point of inflection will be a plateau point, but all plateau points will be points of inflection. Okay? So, a point of inflection here is also a plateau. And notice here, the first derivative doesn't change sign. We're decreasing and then we're decreasing. Okay? So that doesn't change, but notice the concavity or the curvature here changes. To the left here, we are concave up. Okay? We're concave up. To the right, we're concave down. Okay? Now sometimes it can be hard to tell. You know, is it concave up here or is it concave down? Draw the tangent lines, because the tangent lines will actually tell you. Okay? Oh wait, I colored those backwards. Let me fix that so it's not confusing. Here it's concave up. That was blue on the other one. And here's concave down.
How do the tangent lines help you?
Okay, let's look at how the tangent lines help us. Let's look at the two parts where it is concave down. Concave down. We'll put C down. Okay, and this is concave up. Cup. All right, so on the part that's concave down, if I draw the tangent lines, okay, there, and then also here, okay, can you see those? All right, what do you notice about all the tangent lines on the parts that are concave down?
They're aiming down.
What?
I don't know.
They're not all pointed down, but they're all... Let me show you as opposed to where it's concave up. Concave up, tangent, 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 Stay with me here. Tangent, tangent. Here. Notice all the tangents, when it's concave up, the tangents are underneath the function.
Oh, okay, okay.
But on all the parts where it's concave down, all the tangents are on top of the function.
What are tangent?
Tangent lines.
Like
Like first derivative. Like if we found the tangent lines and drew them, when it's concave down, they will all be on top of the function. When it's concave up, all the tangents will be underneath the function.